Okay, the next step in our analysis is to do the differential continuity equation, differential form of the continuity equation. And remember, last time we had derived the Reynolds Transport Theorem, which allowed us to move from a system perspective to a control volume perspective, okay, where we preferred the control volume formulation because it allows us to have this Eulerian frame of reference where we can assign velocities and properties at a point. We're still not there yet because the form of the Reynolds Transport Theorem is integral, and that's given by dB cis by dt is equal to d by dt of the integral of rho b dV over the system. Remember that this was an intensive property and this was an extensive property, and that was shown to be equal to partial by partial t of integral over a control volume of rho b dV control volume plus the surface fluxes rho b u dot n ds. Okay, today we are gonna take the application of the Reynolds Transport Theorem to mass conservation, which said that dm by dt for mass, dm for a system by dt equals to 0, so that implied that d by dt of the integral or a control volume of rho dv plus mass out minus mass in rho u dot n ds is equal to 0. Okay, we did a few examples on that. Today we're going to take this form, the control surface over here, and convert it into a differential form. Now remember the great theorems for the integral theorems. That's what we're going to use here today. Okay, so if you remember those, the first thing we observe here is that we have two types of integrals here. So there's the volume integral and there's a surface integral. And there's also one more problem, and that has to do with this partial by partial t term. If we could somehow write everything in terms of one type of integral, either a surface integral or a volume integral, better to be written as a volume integral, and somehow move this d by dt term into the inside of the integral, then we would have just a single integral over an arbitrary control volume equal to 0. And we can do that exactly. Okay, so let's start by looking at the surface integral of rho u dot n ds. Now remember the integral theorem that tells us that this is equal to the integral over the volume enclosed by this control surface. Remember, our control volume is enclosed by a control surface. So the control surface is identical to the surface that controls the control volume. So this CV over here is the same as this CV over here, but that is equal to the divergence of rho u dV. Now, we had talked about this before, but we applied it to the concept of the integral over the velocity. Okay. Now, in this case, we have the integral over rho u. Okay. Now, we've converted the surface integral to volume integral, so now our continuity equation becomes d by dt, the integral over the control volume of rho dV, plus the integral over the control volume of div rho u dV equal to 0. If only we can move this time derivative to the inside of this integral, then we can combine both of these into one volume integral and then do something really cool with that. So here's what we're going to assume. Since we've assumed that the control volume is fixed in space and time, it's non-deformable, so it's not changing with time. The shape of the control volume is not changing with time. Even if it was, we would have to do something a little bit different for that case. But still, in this case, the easiest assumption to do is to say that the control volume is fixed in space and time. Then this integral over this partial derivative over the control volume can go in because the integral is not changing in time. Okay, so then we have this integral over the control volume of partial by partial t of rho dv, okay, going from here to there, plus the integral over the control volume of div rho u dv equal to 0. Now the next step is to simply take that, so I'm going to write it here again. So integral over the control volume of partial by partial t of rho dv plus integral over the control volume of div rho u dv is equal to 0. Let's combine both of these into a single integral from cv of partial by partial t rho plus div rho u dv equal to 0. Now I'm going to make a claim here and say that the only way that this is equal to 0 is if the integrand is equal to 0. Why can I make that claim? Well, remember when we selected our control volume, we didn't specify what the control volume looked like. Although, yes, we derived it for a rectangular control volume. That was just for the sake of illustration, but we could have derived it for an arbitrary control volume. And this will hold for an arbitrary control volume. And therefore, if this is true for any control volume, then it must be that the integrand is identically equal to 0. And with one jump, you can go from the integral form to the differential form of the continuity equation, plus div rho u equal to 0. Okay, continuity or mass conservation equation. Okay, this holds for a compressible, incompressible flow. There's a simplification for incompressible flow. We'll see that in a bit, but this is really powerful because now we have gone from just an integral formulation where we had to make certain assumptions to simplify our analysis, say for example a certain velocity profile at the inlet and the outlet, to a differential form where we could actually now solve for the density or for the velocity by using this kinematic condition. We still need the Navier-Stokes equations, but this is one of the most important constitutive equations for fluid dynamics right now. So we're going to take a detour now, and we are going to derive the infamous material derivative. We're going to do a preliminary intuitive derivation with a simple example so that you kind of get an idea of what we mean by the material derivative, and then we'll do another derivation just straight from the Reynolds Transport Theorem. So let's assume that there is a factory, so let's say there's just like this big factory over here, and it's got some chimneys spitting out smoke into the atmosphere, and it happens that this factory is close to a river, and there's flow in this river. And assume that we know that this factory is dumping some sort of pollutant or some liquid into the river. So initially it's coming in with this kind of sort of concentration, and then you're going to have the pollutant disperse throughout here. You're going to have a very large concentration over here, and then smaller and smaller concentrations as you go along. So there is a gradient, essentially dc by dx. We're going to assume things in 1D right now before we do it before we extend it to 3D. Okay, so now let us consider a person. Let's say you want to measure the concentration at a point. What you would do, you would send one of your grad students. They would come here, and then they would just kind of throw in a little tool that measures concentration, and we're going to assume that the concentration doesn't change in time. There's only change in space for this situation. So what the person is going to measure over here is over time, with respect to time. If you look at concentration, they're just going to measure a constant concentration at that point. Okay, there is a concentration gradient, so if they do a measurement at another point, they're going to get a lower curve. Now, let's say you send in another graduate student who is going to take a boat. Say the grad student is into boating, and they're going to take a boat. So they're going to be on this kind of little canoe over here. There's a grad student, and they're going to throw in a little same probe to measure concentration. Now, as they approach, as they go through the river, they're following the same velocity of the river. As they approach the region of the concentration, they're going to start measuring concentration. But over here, they're not going to measure anything. So initially, this is what this is going to look like. Okay. Over time, from the perspective of the student on the boat, initially, they're not going to measure anything until they hit, let's say, this point A over here, and then bam, they're gonna get a spike in concentration, okay, and then they're gonna go down like this because there is a concentration gradient, okay? There is a concentration gradient in space. But from the perspective of the boat, they're measuring this with respect to time. Now, we want to make sure that as they approach this point, we're going to call this point B, let's say this is point B over here. Well, that concentration needs to be identical to the one measured by the person in the Eulerian frame. Okay, so now the question is, obviously from the perspective of the person on the boat, there is a change in concentration over time. So there is a dC by dt. And the question is, what is that equal to in terms of the spatial distribution of concentration, and how can we reconciliate the value of dC by dt by with the value measured by the person doing the Eulerian perspective. So what we're going to do, we're going to zoom in a little bit over this region where there is a concentration. Okay, so we're going to assume that this is kind of the gradient of concentration. Over here, a portion in the river. There is C0 over here and C1 over there, and these are spaced by a distance delta x. There's higher concentration over here. C0 is greater than C1, so there's higher concentration over here. So the gradient is like this, dC by dx. Okay. Now, what is dC by dt? Okay, from the perspective of the person on the boat, they're going to be here. They're going to come, they're going to hit C0, and then they're going to hit C1. So from their perspective, dC by dt is the limit as delta t approaches 0, C1 minus C0 over delta t. Now, because this is an infinitesimal distance, we can say that C1 is approximately equal to C0 plus dC by dx times delta x, whatever that gradient is. Okay, so we're going to substitute this here. We get a limit delta t approaches 0 of C0 plus dC by dx delta x minus C0 over delta t. So C0 and C0, they cancel out. So we get this equal to delta to the limit as delta t approaches 0 of delta x over delta t times dC by dx. Now this person on the boat is traveling at the same speed of the fluid flow. Okay, so in a time interval delta t, they're going to travel a distance delta x, so that delta x over delta t is equal to the velocity. or in other words, the distance that they are traveling, delta x, is equal to u delta t. So that means that we just get rid of the limit. We don't need it anymore. This is equal to u dc by dx. That's equal to dc by et. And there you go. This is the relation between what the person in the Lagrangian frame is measuring compared to the actual distribution and of the concentration gradient. Okay. So now you can see how when we do this in 3D, it's easily to extend this to 3D, that this actually turns into a gradient of the concentration, and this actually turns into the velocity vector field. Okay, so this becomes in 3D dc by dt equal u dot grad c. I mean, you can do the same thing in all three directions, and you're going to get three different components. You're going to get u dc by dx plus v dc by dy plus w dc by dz. So you get this kind of version on 3D. Now we haven't said anything about the change in time. So now we're going to assume that we're going to go back to the same river, and we're going to assume that also not only the concentration is changing in space, but that it is also changing in time. So now there's going to be a gradient in space from C0 to C1, and there's also going to be a gradient in time, because C0 and C1 are changing in time. So we're going to take the same region of space, we're going to assign this point C0, and this point we're going to say C1, but also assume that not only there's a gradient, so C0 is higher than C1, but there's also a change in time. So C0 and C1 are both changing in time. So the way we're going to write this is as follows. We're going to do dc by dt is equal to the limit as delta t approaches 0 of C1 at t plus delta t minus C0 at t over delta t. Now, the idea here is that the person on the boat, they arrived at time t, they arrived at position C0, okay? So that's our C0. And then in an increment delta t, they arrived at position C1. They're going to measure something different at C1. Okay, so that's why we have two different subscripts over here, C1 and C0. If they were at the same position, it would be C0 t plus delta t minus C0 at t, but that's not the case because they're moving with the fluid velocity. Okay, so now we have to think about what is C1 at t plus delta t. It is actually equal to C1 at t. So at time t, once the observer arrived at C0, C1 had a concentration called C1 at t. But then once they approached C1, that concentration changed by how much? It changed by dc or del c by del t times delta t. That's by how much it changed, okay? That's the first order, all right? Now, okay, so once we substitute this, we get a limit of delta t approaches 0 of C1 of t plus dc by dt delta t minus C0 of t over delta t. Okay, so now we kind of incorporated the change in time. Now we still need to incorporate the change in space, which is at a given time t, the difference between C1 and C0 was given by what we calculated early on, but we can just show it here for illustration. So we're going to write C1 at t is equal to C0 at t. So that's at the same time. The only change is going to be spatial, plus dc by dx delta x. Okay, so that's delta x over here. Once we plug things in, we get dc by dt equals to the limit as delta t approaches 0 of C0 at t plus dc by dx delta x plus partial c by partial t. I guess I should put partial over here because c is a function of x and time, space and time, delta t minus C0 of t over delta t. So now C0 and C0, they cancel out. And again, delta x, pardon me, delta x over delta t is the velocity. Delta t and delta t cancels out. And in the end, we get dc by dt is equal to d partial c by partial t, that's the local change measured at a fixed point in space, plus the spatial change measured at a fixed point in time. Okay, partial c by partial x. And that is the material derivative. Now in 3D, this becomes, you're going to see the symbol capital C also written. dc by dt is partial c by partial t plus u dot grad c. Okay. And in general, what we say is the material derivative of a given property phi is equal to d phi by dt partial phi partial t plus u dot grad phi. Okay. The idea here is that we are tracking an infinitesimal fluid particle or infinitesimal material point as it goes and flows with the flow velocity. This u here is the flow velocity, and we're assuming that the fluid particle is going to go with the flow velocity. Okay. Now this is very helpful, for applications like you're sending a balloon in the atmosphere, or you have a pressure sensor or some probe that is moving with the fluid and measuring things. And we can derive the same thing for a probe that's moving at a different velocity. So you just take relative velocities. But this is the basic idea of the material derivative. All right. Now, before we proceed with some examples on the continuity equation, we need to take a small detour and discuss incompressibility and what that implies to the continuity equation. We will look at this from two perspectives. So we'll start with the first perspective, and so this is about incompressible. Okay, so again we write the continuity equation, d rho by dt plus div rho u equals to 0. Now let's split this term as d rho by dt plus rho div u plus u dot grad rho equals to 0. Now recall that the combination, this guy, that guy, that's called the material derivative. And remember that it describes how a property changes for an infinitesimal material point. The Reynolds Transport Theorem dealt with a finite-sized material system. This is the equivalent of the Reynolds Transport Theorem for a material point. So what we're going to do, we're going to write this as d rho by dt, material derivative of the density of a material point or a fluid particle, plus rho div u equals to 0. Okay. So we're going to make two arguments for incompressibility. They're both going to mean the same thing. The first argument, okay, so argument 1 for incompressibility, and that is to say that, while the mass of a fluid particle remains constant throughout the flow, a fluid particle is incompressible if its density does not change. In other words, you're not able to compress more material into the same volume. So in other words, rho for a fluid particle is equal to a constant, this implies that the material derivative of the density is equal to 0. Remember, we are following particle path. We're not saying that the density is constant across the fluid, so be very careful about this. Okay, so incompressibility does not necessarily mean that the density is constant throughout the fluid. I'll give you an example. Take a balloon. Take a balloon or a container, and put in it droplets of water, which is incompressible, and droplets of oil, okay, which is also incompressible, and shake them. So the density across this entire container, rho, is not constant in space and time, okay, constant, but for a material element, so for one of these particles, wherever they go, the density is going to be constant. So d rho by dt is equal to 0. But if you pick a point in space and particles are sloshing around, at one point you're measuring the density of the air, one point you're measuring the density of the water, one point you're measuring the density of the oil. So keep that in mind. And in fact, just to remind you that this d rho by dt equal to 0, that tells you that for an incompressible flow, d rho by dt plus u dot grad rho is equal to 0. Okay? Now, this, by virtue of the continuity equation, this necessarily implies, this also necessarily implies that div u is equal to 0. Okay? Div u is equal to 0. Just plug this back into the continuity equation from the previous page. Set this guy equal to 0. You get rho div u equal to 0. And since rho is non-zero, then div u must be 0. Now remember, div u is the net outflow of volume at an infinitesimal point. And when we say div u is equal to 0, what we're really saying is that there's no change in the volume. There's no change in the volume. So you can change its shape, etc., but it's going to retain the volume is going to be constant. Therefore, div u is equal to 0. The second way that we are going to prove incompressibility is we're going to go after this condition, and we're going to derive this condition from the change of a material volume. Okay, so we're going to consider first a very small material volume. Very small material volume. Let's call this point O for origin. Okay. Now, in reality, you're going to have a velocity over here, u and v, etc., and the velocities here may be different due to gradients, and the general motion of this volume is for it to rotate and translate, etc. So if there are no gradients, it will just move along, right? But because there are velocity gradients, the velocity over here is going to be a little bit different than the velocity over here. So if we call this distance delta x, okay, and this entire volume delta v equal delta x, delta y, delta z, right? So this is going to be delta y, and delta z is going to be in the other direction, right? So delta z, okay. For the sake of the illustration here, we're just going to assume that there is a single velocity gradient in the x direction. So in other words, v velocity does not change from this point to that point. However, it changes from this point to that point. And we're going to call this velocity as u plus du by dx times delta x. Okay, so that's an infinitesimal approximation based on the Taylor series. This du by dx gives us the rate of change of the velocity in the x direction. Okay, and same thing over here. We're going to assume that this is also equal to u plus du by dx delta x, because we're going to assume this point 2 has an axial velocity of u. So in a time increment delta t, this control volume, this not control volume, this material volume, infinitesimal material volume, is going to move just a little bit. Okay, so it's going to move just a little bit. Okay, due to this velocity, this difference in velocity. Okay, and this movement, measure this distance. What is this distance? Okay, it's actually du by dx times delta t. Okay, that's this distance. Okay, that's by how much this is actually, that's the distance is actually, so this du by dx meters per second times second, so that is going to give us meters. Okay. So this distance is actually, yes, du by dx delta x, right, times delta t. That's this little distance over here. Okay. Now, what is the difference between the two volumes? Right, we just simply take the difference and it's going to be equal to this shaded area. So the change in delta v, so change in delta v is equal to this volume, which is delta x du by dx delta t. So that's the this length times delta y times delta z. So it is equal to, but remember delta x, delta y, delta z is equal to delta v. So it's equal to du by dx delta t delta v. Okay, so that's the change in delta v. Now the rate at which this volume is changing is given by the time derivative of this change. So if we take d delta v by dt, that is going to give us d by dt of du by dx delta t delta v. Now in such a small increment of time, what we get is equal to delta v times du by dx. Okay? Because that is in the limit as delta t approaches 0. In other words, the way we can define this is d delta v by dt is the limit as delta t approaches 0 of du by dx delta t delta v over delta t. Remember, because that's the change. So this is equal to the volume at t plus delta t minus the volume at t, and this is that difference, and we divide by delta t, so we get delta v du by dx. Okay, so we're starting to get to the point where we can relate this to the dilatation. And you're starting to see the first elements of the dilatation. Remember that the dilatation du is equal to du by dx plus dv by dy plus dw by dz. This is the first element of du. And in fact, if you repeat this same analysis and you assume you do the same thing, but you do it for all three velocity components, u, v, and w, and you extend the cube appropriately, what you're going to get is d delta v by dt is equal to delta v div u. Now, a better way to write this is to do the rate of change of volume per unit volume, so we don't depend on the size of the volume. So we typically write this 1 over delta v dv by dt is equal to div u. Now we make the argument that is equivalent to the density argument that we made, the material derivative, early on, and we say that for an incompressible flow, a material volume cannot be compressed. So therefore, compressible necessarily implies that d delta v by dt is equal to 0, which implies that div u is equal to 0. Okay, so we already derived the material derivative using this kind of intuitive approach of the example of the person making a measurement in a river, and that where there's a plant dumping some pollutant with a concentration, etc. Now I want to show you another derivation for the material derivative based on the Reynolds Transport Theorem. So recall that the Reynolds Transport Theorem, we wrote that for a material system, for a finite size material system. So we had d by dt, the integral over the system volume of some rho b dv, and then we expressed that in terms of a fixed control volume, d by dt of rho b dv, plus integral over the control surface of rho u b dot n ds. Okay, so the problem with this integral is, although we can turn this right-hand side into a volume integral over the control volume, you get d by dt rho b plus div rho b u dv. The problem is that this control volume is different than the system volume. Why? Well, when you think about it, the Reynolds Transport Theorem is telling you how the integral of a certain property over a finite sized material volume changes as the material element moves through the fluid, as the material volume moves through the fluid. Now, in principle, that is essentially the material derivative, but applied to a finite sized collection of material points, which is the material system. So in principle, if we shrink the material system to an infinitesimal point, so V system goes to 0, then we should recover the material derivative. So we can do this on the left-hand side, but on the right-hand side, what are we shrinking? The control volume, and how does that relate to the system volume? So what we really want is to have the same volume on both sides. Luckily, there is another version of the Reynolds Transport Theorem, or more specifically, something called the Leibniz differentiation under the integral formula, that says that d by dt, the integral of some quantity v over a volume v, t, that changes through time, is equal, interestingly, to the same form of the Reynolds Transport Theorem. And written in volume form, you get d phi by dt plus div u phi dv. That's the same volume. So now we have something we can work with. In the limit as v of t approaches 0, very small limit, then we can say that the property phi is constant across that small volume. So then we could say that d by dt of phi dv is d by dt of phi delta v, very small volume that we will take all the way to 0, equal to the same thing, d phi by dt plus div u phi times delta v, because this entire quantity is constant across the small volume. Okay, so now what we can do, we separate the left hand side as phi d delta v by dt plus delta v d phi by dt equals to d phi by dt plus div u phi. Now there's a delta v over here. I'm going to divide by delta v, so we get a delta v, and this cancels out. So now you can see the material derivative show up over here. This is the material derivative. Okay. Now what we can do here is take this phi times 1 over delta v d delta v by dt plus d phi by dt equal partial phi by partial t plus div u phi. Now what is this guy over here? Remember, this is the rate of change of a material volume per unit volume, and we had shown earlier that this material derivative, by the way, we had shown earlier that this is actually equal to the dilatation, div u. So then, once we substitute, we get phi div u plus d phi by dt equal partial phi by partial t. Now this guy over here, we can replace with u dot grad phi plus phi div u, just distributing the dot product. And what we get is plus u dot grad phi plus phi div u. Now these two guys cancel out very nicely, and you get the material derivative derived from the Reynolds Transport Theorem. It's u dot grad phi.